In this video, I want to start our exploration of the Baxandall tone control circuits by looking in more detail at a treble tone control circuit. This is the circuit we'll be looking at. You can control the gain at high frequencies by adjusting the position of the wiper on this potentiometer. The gain at low frequencies is a constant and pretty much always equal to -1, since this filter is based on an inverting op-amp. So here is the circuit. And the first thing I'm going to try and do is convince you that at low frequencies, this circuit always has a gain of -1. And the assumption that we make to do that is that at sufficiently low frequencies, the impedance of the capacitor will be much greater than the impedance of any of these resistors. Which means that the current flowing down through the capacitor, with its very, very large impedance at low frequencies, will be negligible compared to the currents flowing elsewhere in the circuit. So we can approximate the circuit like this. Just take the capacitor out of the circuit. It's not doing anything. Now there are two ways that current can flow from the input to the output in this circuit, either through these three resistors or through these two 100k resistors. It's the two 100k resistors that are interesting, because the way the op-amp is wired up, it's an inverting amplifier, and the non-inverting input is tied to ground, 0 volts, which means that as long as the op-amp is in its linear region, we can assume that the inverting input will be at 0 volts as well. Well, if the inverting input is at 0 volts, then this point in the circuit here must be at 0 volts, which means that the current through R4 will be given by Vin minus 0 over R4. And that must be equal to the current through R5, since no current flows in to an ideal op-amp. And the current through R5 would be the voltage across R5, which is 0 minus V out, over R5. But the way we've built the circuit, R4 and R5 are equal. They're both 100k. So they cancel out. And that just gives us V out equals minus V in. All the other three resistors up here do is cause a bit of extra current to flow from the input to the output, or vice versa. They don't affect the gain of the circuit at all. So that's what happens at low frequencies. V out is just equal to minus V in. We have a gain of 0 dBs. Now, what about at high frequencies? Well, at very high frequencies, we can make exactly the opposite assumption about the capacitor. We can assume that the impedance of the capacitor is so small that it effectively behaves like a wire. Its impedance is negligible compared to the other impedances in the circuit. And if I make that assumption, then the circuit simplifies to this. Now, at full boost, that would mean that I would have V in coming in here, through a 1k resistor here, a 100k resistor there. The wiper of the potentiometer would be all the way to this side of the potentiometer, so it would be taking out the voltage at this point here and forcing that into the inverting input of the op-amp. All of the 10k resistance of the potentiometer would be on the other side of the wiper. It would add up directly with that 1k there, and we'd end up with a circuit like this. Well, this is a 1k and a 100k in parallel, and this is effectively 11k in parallel with a 100k resistor. So I could replace this resistor network and this resistor network just with their equivalent resistance, and that would produce this. And this is a standard inverting amplifier with a gain Vout over Vin of minus 9.91 over 0.99, approximately minus 10. So it's about a 20 dB gain. If we do a similar thing at the full cut, then the inverting input of the op-amp is effectively connected to this point in the circuit here, as all of the 10k resistance in the potentiometer is now on the other side of the wiper. So now we have this resistor network on the input side and this resistor network on the feedback side, and that produces this. And this is a non-inverting amplifier with a gain of minus 0.99 over 9.91, approximately 1/10, which comes out to be minus 20 dB. There's one more special case to consider, and that's this one with the tone control set midway. Now, if you consider the voltage on both sides of the capacitor, on this side of the capacitor, the voltage is going to be halfway between Vin and Vout, because this resistor is equal to this resistor. On the other side of the capacitor, the voltage is also going to be halfway between Vin and Vout, because you've got 6k on this side and 6k on this side. So with the same voltage on both sides of the capacitor, there's going to be no current flowing through the capacitor, so effectively the capacitor is not doing anything at all. Here we have exactly the same resistance on the input side as we have on the output side, and that would result in Vout over Vin being -1 at all frequencies. In other words, a completely flat frequency response. If we want to know what the response of this circuit is at other frequencies, and when the slider of the potentiometer is not set right in the middle, then we have to do a full nodal analysis of the circuit. As with a lot of active filter circuit, this ends up being a rather tedious exercise. However, this is the answer that you should get once you've gone through all of the algebra. Alpha is the position of the slider on the potentiometer. It moves from 0 on one side to 1 on the other side. Now you can see here that we have a single 0 and a single pole. And the pole occurs when j omega is minus R1 plus R2 plus R3 all over C R5 plus this lot. And we have a single 0, and the 0 occurs when j omega is R1 plus R2 plus R3, actually minus that lot, divided by C R4, R3 plus alpha R2. So the position of the pole and the position of the 0 are moving when the slider is moved along the potentiometer track. As alpha increases, the break frequency of the 0 decreases, and the break frequency of the pole increases. So they kind of move against each other, like this. When alpha equals 0.5, as long as R1 equals R3 and R4 equals R5, the pole and the 0 are at exactly the same frequency and cancel each other out. You can plot the break frequency of the pole and the 0 against the value of alpha, and you'll end up with a curve like this. Now what the Bode approximation has showed us is that a 0 will tend to increase the slope of the amplitude response by 20 dB per decade, and a pole will tend to decrease the slope by the same amount. So if we have a 0, which is, say, at that point there, and a pole at this point here, then we would expect the Bode approximation of the amplitude response to do something like this. If the 0 then moves to this point here, and the pole decreases, so its break frequency is now at this point here, then the Bode approximation of the amplitude response would now do this. Go a little bit further, flat, up at 20 dBs per decade still, but stop sooner when it gets to the break frequency of the pole, and then head off like that. And we end up with a filter which has got a reduced amount of gain at high frequencies. If the pole has a lower break frequency than the 0, then the amplitude response will start going down until it hits the 0, and then continue horizontally when it hits the break frequency of the 0. The whole family of curves ends up looking like this. Next time, we'll have a look at the bass tone control.